Greetings, Math Champions. Welcome to Math with Janet. I'm Janet Moore. Today's topic is the formula for the area of a circle. We are going to do part one of a two-part activity called Square Peg in a Round Hole. This activity is designed for 7th grade students and targets the standard 7.G.B.4. The math supplies that we are going to need for this activity are these printouts from the website. You can download these and print these out from mathwithjanet.com. We will also need some colored pencils or colored markers. We are going to need some 4-inch squares cut out of cardstock or cardboard or something sturdy. Scissors are optional but very helpful, and also optional but helpful are centimeter cubes. Base 10 block small cubes work just perfectly for what we need to do with them. In previous grades, even as early as 3rd grade, students found the areas of rectangles and other shapes composed of rectangles by tiling them with unit squares and looking for patterns in their tiling. Then in 6th grade, students had to get creative to find the areas of other shapes. Shapes like triangles and parallelograms and trapezoids that don't always have right angles. In order to do this, students decomposed those shapes and rearranged the pieces, composing them into a rectangle that they could then find the area of. Now in 7th grade, for the first time, students will be challenged to find the area of a region that doesn't have any angles at all, to find the area of a region with a curved boundary, a circle. This is no easy task. It's literally trying to fit square pegs into a round hole. In part one of this activity, students will unitize the concept of r squared in order to approximate the area of a circle. If the word unitize is a new term for you, pause this video and go watch my video on unitizing so that you understand its concept before you proceed. Then in part 2 of this activity, students will decompose the circle into several pieces. And much like they did in 6th grade, they will try to rearrange those pieces to form a different shape that's more familiar, that they can use then to calculate the area. Okay, Math Champions, it's time to get started. Let's play math. These two printouts have circles that are the same size but printed on a different size grid. This paper has a 4-inch grid so that it will match the 4-inch square tiles that we cut out earlier. And this paper has a centimeter grid so that it can match with the centimeter cubes that we have set aside. Let's start with the larger grid first. Notice that the question at the top of the page is not what is the area of the circle, but rather it asks how many unit squares would it take to fill the circle. We don't want students to avoid the problem solving involved in the activity by doing random calculations that they may not understand. By asking how many unit squares it would take to cover the circular region, we are beginning with the meaning of area before we use the term area. If the radius of the circle is 1 unit in length, then this square up here, built off of that 1 unit length, must be a unit square, or 1 square unit. Each of these cardstock squares that we cut out has a length that matches that radius, which means that each of these cardstock squares is a unit square. So now the question that we want to ask is, how many of these unit squares would it take to cover the circular region? Since this is a difficult question to answer perfectly, it might be more helpful to ask students for 3 estimates. It doesn't take too much for students to see that a good high estimate is going to be 4 unit squares. The too low estimate probably will have a little bit more variation in student answers. Some students might just go with the easy out and say that 1 square unit is too low, and technically they are correct. If you challenge them to get a little bit more creative, several of them will look at that circle and they will say, well, I think I can cut that square in half across that diagonal. And the region inside of there is essentially composed of 4 triangles that each represent half of a square unit. And so 2 square units is a good low estimate. At this point, we can ask our students to make their best guess and decide what their just right Goldilocks estimate is. In order to do that, they have to consider how much space is there between the low estimate and the circle, and maybe compare that with how much space is between the circle and our high estimate of 4 square units. Doing a quick visual comparison, most students will say that their just right best guess Goldilocks estimate is going to be right in between our low estimate and our high estimate, and they will call that 3 square units. It's probably valuable at this point to ask students if they think that the exact answer is a little bit more than 3 square units, a little bit less than 3 square units, or exactly 3 square units. But at this point, we're just taking a poll about their guesses and their visual estimates based on what they see in their diagram. We're not going to get too far into deciding exactly what that just right perfect answer is going to be yet. Instead, we're going to stick those too high, too low, and just right estimates onto that paper for reference later. And then we are going to switch to our smaller sized grid and do a little bit of investigating with it. This time, our units are smaller. Each of these is our new unit that we are going to consider when deciding how many unit squares it will take to fill this circle. Because that's a centimeter grid, we can use centimeter cubes to tile as much as we can of this circle. A lot of 7th graders won't have the patience to do this for very long. Several of them will abandon it and just go to counting these square units, either one by one or by grouping them into larger chunks. One nice thing about having a smaller grid is that we can get a more precise answer. If you give students some time to count as many of these individual squares as they possibly can, they will eventually be able to count and estimate that there will be over 300 of these unit squares inside of this circle. That's a helpful thing to note at this point in the activity because it's going to relate back to the first part of our activity with the larger grid. Once again, as they are doing this initial count, we're going to ask students to give us an estimate based on their count that's too high, an estimate that's too low, but still pretty close, and an estimate that is their Goldilocks best guess at what is just right for this circle. After students have made their estimates using these smaller unit squares, we are going to draw in the vertical and horizontal grid lines that show a couple of the diameters of this circle. We want to point out that a couple of those grid lines cross the center of that circle and form a radius that is horizontal and a radius that is vertical. That's going to be helpful for what we want to do next. At this point, we can count to see that the radius of this circle is 10 units in length. If we use that radius of 10 units as the side of a square and we build this square up around this section of the circle, we get a square that happens to match our cardstock squares that we used earlier. This time, Our cardstock square does not represent 1 unit square though. Instead, this time it represents all of these little unit squares in there. And how many are there? Well, it's 10 by 10. It's 10 rows of 10. This right here, this region, and subsequently this big square represents 100 of those little tiny square units. And now that we've recognized that, we're back to the same question we had with the larger grid. How many of these 100 square unit sections would it take to cover the entire circle? And once again, our answer is 4 is too high, 2 is too low, and when we compare the region between our too low and the circle's edge with the region between the circle's edge and our too high estimate, we might say that 3 of these would give us a pretty good Goldilocks just right estimate. So this time our too high estimate is 4, but it's not 4 square units. It's 4 of the 100 square unit blocks. Our too low estimate, again, is 2 of these blocks. And so our just right Goldilocks estimate is about 3, but again, not 3 square units, 3 blocks, 3 groups of our 100 square unit section. So what does this mean and how is this helpful to us? We're going to go back to our large grid one more time. This time, we're not going to consider our radius as just being 1 unit in length. This is our radius, and we're going to call it r units in length. Which means that when we build up this square around it, whatever that radius is, this square is going to have r times r. Remember, this is also a radius. So this is r units in length. That is r units in length. This square is going to have r times r square units inside of it. So we have r squared square units in that region. All of a sudden, this same cardstock square that we were using earlier can now be called r squared. No matter what that radius is, this becomes a region that has r squared square units. And whether you realize it or not, what we've just done is we have unitized the concept of r squared. R squared is not just some random calculation, but it's actually this square region right here, the square that we built by using the radius of the circle as its side length. And now we're back to the same question that we've been asking every step of the way. How many of those square tiles, each of them representing r squared this time, how many of them will it take to cover our circle perfectly? Once again, we run into the same situation. 4 of these r squared blocks is too high of an estimate. Once again, cutting along the diagonals and considering this region inside, 2 of those r squared blocks is too low of an estimate. And when we compare this extra space between our too low estimate and our circle's boundary with this space between the circle's boundary and our too high estimate, our just right Goldilocks estimate, it's about 3 groups that are each r squared. So the space inside of this circle, the region inside of there, is approximately 3 r squared square units. The area of this circle is approximately 3 r squared. If you want to at this point, you can bring back our small grid and bring back some of the student estimates, especially if they did a really good job of counting with that smaller grid and if they confirmed that it ended up being a little bit more than 300 square units. If some of the students notice that, you can use that point right now to say, hey, this ended up being a little bit more than 3 of those R squared blocks. So we can probably say that the area is going to be a little bit more than 3R squared, and probably not exactly 3R squared, and definitely not less than 3R squared. But until we do the next part of our square peg in a round hole activity, we won't be able to say for sure exactly what that quantity is going to be. Be sure to watch part 2 of the square peg in a round hole activity, in which we decompose the circle into several pieces that we can then rearrange to form a parallelogram and eventually a rectangle, and to discover that the area formula for a circle is pi r squared. This has been Math with Janet. I'm Janet Moore. Thanks for playing math with me.